So here's the final dual path architecture. We'll talk over this architecture in this video, and in the next video we'll start building it up in Logisim. So we'll start off at the top here with our inputs, which are our X and Y. We have our add and subtract button. So if the subtract is pressed, then the Y value gets negated. So if the Y value was a negative, it becomes a positive. If it was a positive, it becomes a negative. We then go in and we make a comparison with the exponent, and if we need to, we swap the exponent so the exponent of x is always greater than or equal to the exponent of y. So on the left hand side we have the near path, and on the right hand side we have the far path. So let's talk over the near path first of all. Now we only use the near path whenever we do a subtraction and there has been a cancellation. So in that case, we take the mantissa value for x and the mantissa value for y. Now this cancellation will only occur whenever the exponent value is a value of 0 or a value of 1. So it means that the exponent will shift by either a factor of 0 or a factor of 1. So equivalently, it means that the mantissa of y will either shift by a factor of 0 or a factor of 1. So this is a possibility of a 1-bit shift, and we get the control of that shift dependent on the exponent value here. Now looking at these three blocks here within this yellow box, this provides us with the subtraction. But we said previously we want to subtract and ensure that we actually get a positive result, because the positive result in 2's complement is going to be the same as just a normal binary number. So we test the mantissa for x minus mantissa for y and mantissa for y minus mantissa for x, and depending on which one is positive, it will pass that through via this multiplexer. We then do the leading 0 count and the shift. Now the leading 0 count value will also be passed on to the exponent, so the exponent will decrease by this leading 0 count, and it will give us the final exponent value here. And after this leading 0 count and shift, the mantissa will then be passed out. And then we join the three together, that is, we concatenate them. So we take our sine, our exponent and our mantissa into just one block. And then it goes through this multiplexer, and there's a choice made by this multiplexer of the close path or the far path. Now sometimes you'll see it called the close path. The close path is just the near path, okay? So sometimes it's called close and sometimes it's called near. Now on the right hand side here, we're going to have all of the other options. So in all of the other options, we take a copy of the mantissa for x, because we're assuming that the mantissa for x is the largest value, because it will have been swapped here in order to ensure that that is the case. We then go through either the addition or the subtraction algorithm, and again we get a control bit here which tells us which one we're going to be using. We also take a copy of the mantissa for y, and we have to shift it. So we're going to have to shift it by a factor of ex minus ey in order for us to do the addition or subtraction. We then pass the output here through the sticky bit. Now we've not talked about this before, so this is part of the rounding, but we'll get to this in a different video. And once we've done the adding or subtracting, we then go through the rounding and the normalization. We then output the value for our exponent, Ez, mantissa, Mz, and then we join on to the sine bit, which is given by Sz, so we concatenate these three together. We then pass this into the multiplexer, and again we make our choice. So If there has been a subtraction and the value of MR is less than 1, then we're going to choose this near or the close path. And if the opposite is true, that is, there hasn't been a cancellation, then we're going to use this far path here. And our output's going to come out at the bottom, which is x plus or minus y. Now, obviously, there's a few extra things that we're going to have to add in, which we haven't put into this diagram because it just clutters it up. For example, in the IEEE 754, we have our hidden bit, which has to be added and also subtracted off. But we'll see that whenever we start building it up in Logisim. So it's been a long path or road in order to get here, but we have covered the adding and subtracting theory in minute detail, and I doubt if you'll see it described in this detail in any other course. In fact, I'm pretty sure you'll be lucky to find any other course that describes it in any particular detail. So thank you for listening. I'll get you on the next video. Goodbye.